Hello everyone. Today we are going to talk about quantum entanglement. Now granted it is a very complex concept, I'll try to explain it in as simple way as possible using bare minimum quantum mechanics. Now I can guarantee you that at the end of this video, for majority of you, the idea of quantum entanglement will be absolutely clear. Alright, before going into quantum entanglement, let's look at the thing called quantum states. Now if you separate these two terms, quantum stands for anything of atomic dimension. Right, that is 10 to the power minus 10 meter in size. And state is simply the state of being. Let's say someone is laying on a bed. What is their state? They are laying down. Someone is standing under a tree. What is their state? They are standing. Alright, so when you combine this, simply put, quantum state is nothing but the state of the quantum particle. Like what is it doing? Now here we are looking at a 2-electron system. Alright, these both electrons, they are independent of each other. And we are looking at the spin of these 2 electrons. Okay, now an electron can take 2 spin. Either it will be up or it will be down. Alright, so we can denote these spin up as A up and spin down as A down. Similarly, the case will be for this electron B. Now 50% of the time the electron without any external factor is seen in state up, and 50% of the time it is seen in state down. Thus we can write the complete state of electron A as small a and b are some arbitrary constant. So A up plus small b, A down. This is the state of this electron. Now the significance of this small a and b is that A square is the probability of finding the electron in A up state, and similarly B square is the probability of finding this electron in A down state. Now together this whole probability has to be 1. Alright, so in quantum mechanics we make probability from 0 to 1, that is equivalent to 0% to 100% probability. So A square and B square together will be 1. Also we know that since both states are equally likely, A square should be equal to B square, therefore 2A square is equal to 1, or A will come out to be 1 by root 2. Thus we can rewrite this equation as A is equal to 1 by root 2. I'm using a different notation, A down and A up. Alright, similarly we can use for B 1 by root 2 B down plus B up. Alright, now if we want to combine these two equations, so here we can write psi or threshold equal to, similarly the arbitrary constant A up plus A down, again arbitrary constant B up plus B down. Alright, so simply you have to multiply these two states and you can get the combined state for these two independent electrons. And we are talking about spin of the electron. Bear in mind. And this is up and down only when we are measuring vertically. If we are measuring say horizontally, the spin would be left or right. Alright, now we are looking at entangled quantum states. So what are entangled states? Earlier we saw 2 independent electrons. Now we are looking at one system with 2 electrons. And let's say the net spin of this system is 0. That is, if one electron is in up state, the other is in down state. And hence the net spin is 0. Now what we are doing is we are separating these 2 electrons by some distance, be it an inch, a feet, or maybe even a light year. But we are separating it such that these 2 electrons, they are still entangled. So what is going to happen? This net spin is still going to be 0. So if electron A is in up state, electron B has to be in down state, and thus net spin is 0. Similarly, if electron A is in down state, B is in up, and net spin is equal to 0. So here we write the equation for this entangled state, psi is equal to the arbitrary constants and then A up, B down, arbitrary constant, A down, B up, because this is the only state that is possible. You cannot have a system where A is also up, B is also up, because then the net spin will be 1 or minus 1. I mean, if it's down, it will be minus 1. So since this is not possible, we only have this two, and thus this is the entangled state. Again, the probability is 50% for this, 50% for this, and hence it will be, the constants will be 1 by root 2. Now let's say I measure it. Okay, I don't know exactly right now what state A is in, but upon measuring I find that A is in a down state. What can you tell about the state of B? Is it up or is it down? It has to be down, right? It has to be up, right? There's no other way, because the net spin has to be 0. Similarly, if we measure A and it's in up spin, B has to be in down spin, because the net spin has to be 0. However, in this case, the earlier case, what we see here is that, let's say we measure A and we find that A is in a up state. What can you tell me about the state of B? You don't know. There's still 50% chance that it's up and 50% chance that it's down. Why? Because this system is not dependent upon each other. B can take independent spin, A can take independent spin. While here, their spin are related to each other. These two electrons, they are related to each other. So physicists have always used this thought experiment where they involve two people, one by the name of Alice and other by the name of Bob. However, since we are making this video for Indian students, let's call these two people by some desi name, Sharma ji and Malhotra ji. Okay. Now what we do is we give them each an electron and we ask them to measure the state of electron every 5 minutes. And they do this for 100 times, okay? And let's consider there's no error in measurement. There's no error, no external factor is involved. Now let's assume two cases, case 1 and case 2. Now what happens is, in case 1, Sharma ji gets a up state for A and he gets a up state for B. Again, he gets up state for A, down state for B. Then down, and then down, and then up, and then down. Alright? So what we see, at one time they both have similar spin, and at other time they have spin in opposite direction. So these two instances occur 50% of the time. And in case 2 what we see is, when Sharma ji gets up, Malhotra ji gets down. Sharma ji gets up, Malhotra ji gets down. Sharma ji gets down, Malhotra ji gets up. Sharma ji gets up, Malhotra ji gets down. So almost every time the spin is in opposite direction. So this happens every time. So 100% of the time the spin is opposite. While here 50% of the time the spin is opposite. While 50% of the time the spin is same. So then they come together for a cup of coffee and they compare their notes. And they share their observation that in case 1, 50% of the time the electrons are in opposite spin, while 50% of the time they have the same spin. While in case 2, 100% of the time the spin is always opposite. They can safely conclude that in case 2 they are dealing with entangled electron. While in case 1 this is not entangled. So this is how they find out if the system is entangled or not. So in simple terms, entanglement is nothing but when two parts of the system, they are not independent of each other, rather their state is determined by what state the other is in. That is, if I know A is up, I with certainty know that B is down. Let's look at some of its analogy that we see in Bollywood. Now in movies you see that when hero और heroine एक दूसरे से अलग हो जाते हैं, let's say अलग अलग टाउन में हैं दोनों, और रात में जब सोने जा रहे हैं तो जब हीरोइन की आंख खुलती है उसी समय हीरो की भी आंख खुल जाती है. ऐसे सीन कट होता है, पहले हीरोइन को दिखाते हैं फिर हीरो को दिखाते हैं. फिर हीरोइन करवट बदलती है और उसका हाथ हीरो वाली साइड जाता है बेड के जो खाली है, and then she feels sad. Again, exactly at the same time, hero also changes the side of bed, और जब उसका हाथ जाता है he also feels that bed खाली है and he gets sad. So what is happening here? when the state of one is changing, it is affecting the state of other. So they are both entangled. Okay. Same you can think of in Jurwa movie. When Salman Khan was born, they were both entangled. So if one gets kicked, the other flies across the room. Right? So the state of one affects the state of other. That means they are not independent of each other. They are correlated. And that is how Bollywood incorporated the application of quantum entanglement before, like us physicists, they did. Anyway, coming back to the subject. This is same thing that I've written. One gets sad, the other gets sad. So Einstein described entanglement as spooky action at a distance. So let's see what happened here. So the idea of entangled was floating around since 1930s. Einstein also dabbled in quantum mechanics. And when he noticed that this exchange of information between two entangled states is almost instantaneous, he described it as spooky action because it violated the fact that this exchange is faster than the speed of light. C denotes the speed of light. Okay, and as per Einstein, when he gave the theory of relativity, he said nothing can travel faster than the speed of light. So Einstein was flabbergasted. This was a real WT moment for Albert Einstein. So he, together with two other scientists, Podolsky and Rosen, came up with an interpretation, and he said there is some hidden variable involved. So according to him, there's no exchange of information. It's the information was already there. We just don't know it, and it's coming out when it's needed. Now, with an analogy, I'll try to explain hidden variable as well. So let's look here. Let's say you bought two brand new wallets, and they are both completely empty. And you have a 10 rupee note with you. So you give the wallets and this 10 rupee note to me. And I asked you to close your eyes. And then I put this money in one of the wallets. I didn't tell you. After a while, I tell you to open your eyes and pick any one of the wallet. Let's say you picked the wallet A, which is empty. What can you say about wallet B? You can say the 10 rupee note is in wallet B. Unless, of course, I'm not a neta who took your money and put it in my pocket. You can say with utmost certainty that this 10 rupee is in wallet B. Alright? So this is what hidden variable is. You didn't know that the 10 rupee note is in wallet B, but just by the virtue of knowing that it's not in wallet A, you know that it's in wallet B. A similar experiment for this can be, say you have two balls, one is red, other is blue. You put both these balls in two different boxes, and then without telling you, I swapped this box's position, and then I asked you to pick one of the boxes. Let's say you pick a box with the blue ball. Now you know that the other box must have a red ball. So this is the idea of hidden variable. However, this idea of hidden variable was disapproved by a person named John Bell in 1964. So Bell did a series of experiments which disapproved the idea of hidden variable. There were some loopholes in his experiment, and in the last decade, that is, I think around 2016-17, scientists with almost 100% certainty proved that there's no such thing as hidden variable. So that leaves us with the only option that yes, there is exchange of information between the entangled states. So that means two things. First, Einstein was mistaken. A shock for the scientist, and that's why it took from 1964 till 2016 to prove it with certainty, because no one actually wants to believe that Einstein can make mistakes. But apparently he did. Now that means that there's an exchange of information, and this exchange is faster than the speed of light. Actually, some scientists in China, they calculated the speed, and they found out that it's almost 10 to the power 4 times faster than that of light. And like they also said there may be some error in our measurement, and this actually may be even higher than 10 to the power 4 times. So, but yeah, the idea is that this exchange of information between two entangled states is faster than the speed of light. So now the question arises, does that mean that we can actually achieve faster than light communication using quantum entanglement? Now let's see. We were talking about Sharma ji and Malhotra ji, okay? So say Sharma ji did his measurement and he found some results, okay? And Malhotra ji also did his experiments and he found certain results. Now they have to actually communicate with each other because they can't predict that the particle is in up state. It's random. Quantum mechanics is random, okay? The electron can be in up or down states. You don't know that. When you measure it, you find out that yes, it is an up state. And it is only then with certainty you can say that if there is entangled electron somewhere else, that it is in down state. Or up state, whatever kind of entanglement you're dealing with. So actually this, they have to communicate with each other. Now how are they going to communicate? Well, if they sit over coffee, it's going to take a while. They will have to take a plane to meet and set up. So let's say they call. For the 30 seconds of the call, they'll hear the COVID warning. Hamara desh COVID mahamari se guzar raha hai, blah blah blah. Anyway, ultimately, they will have to use the existing mode of communication to exchange their ideas. Alright? And that's why it is not possible to use quantum entanglement for faster than light communication. I'll give you another example. Like let's say your friend is going to US, okay? And you both have a pair of electrons and they are both entangled to each other. Let's say you tell your friend that if you meet a celebrity like a Hollywood star, let's say if you meet Scarlett Johansson or Iron Man, send me a upspin. Okay, so if you meet Iron Man, change your electron to upspin. Now can you change this electron to upspin? No. You measure it, it's in upspin, good. You measure it if it's in downspin. Even if you have met Iron Man, you cannot change its state. Alright, so your friend here, they don't know what is the state of your electron. It can be up, it can be down. Now, if you try to force your electron to change into a up spin, that will break this entanglement. Okay? So you cannot force a state. And since quantum states are completely random, unless and until you force them, you cannot actually send a structured message to someone. And hence you'll actually need to use the mode of communication which is available to us right now. We don't know what will happen in future. Say 100 years down the line, maybe we can change this state. We can force the state without breaking the entanglement. But right now it's not possible. Then a big question comes. Why are we even wasting our time when faster than light communication is not possible, when we actually cannot communicate using quantum entanglement? Because you see here there's a big fat no. Let's look at some of its application. So the first and the biggest one is it will help in better understanding of quantum physics. Now we are trying to understand our universe and it's not easy. We have so many models. We have classical model where we deal with big objects like us, ball, cars. We have quantum model to study smaller objects like atoms and electrons. So better understanding of quantum physics will mean better understanding of our universe. Second is quantum computing. This is the future of computers and it relies on using quantum entanglement. Third is quantum encryption. That is sending data which is encrypted. It also includes quantum communication, and this uses the principle of quantum entanglement. In fact, you must have read that China has achieved quantum encryption and they have sent quantum satellites in space. Fourth is quantum teleportation. So here the information from one place can be transmitted. I don't know in future if we can, like if humans can teleport, you know, in Star Wars or in Star Trek movies, you must have seen people teleporting from one place to another. And lastly, quantum microscope. This has been realized very recently, I think this week itself. So it will help us better see the biological structure, because earlier the laser light that we used actually destroyed the living sample that we processed. So using quantum microscope, we can better examine these living samples without destroying them. So these are some of the applications of quantum entanglement. So I really hope this idea was clear. Entanglement is nothing but when two states are not independent of each other, rather they depend upon each other. And we have also discussed its limitation and application. Thank you. Have a good day.